Good afternoon, everybody. Welcome to class today. Thank you for joining me, whether you're watching live or you're watching the recording. I appreciate you all watching. We're going to talk Module 1 stuff today, which is thinking like a programmer, just trying to get us ready for the journey that we're about to take this semester. So we'll have a quick discussion of thinking like a programmer, maybe some discussion on approaching bug fixing and sort of the mindset that we have to enter into. And then we'll end our time this afternoon with just a really quick demo of the platform, just to make sure that we all understand what we're all using and how everything works and stuff like that. But before we get into that, just a really brief explanation of why there was no live class yesterday. Some of you might know, but I would bet many of you don't know. Or well, maybe more of you probably know about the esports initiative here at CCC. Getting an esports team or teams up and running for this semester to compete against other two-year colleges from the area. And as it turns out, I'm the one that's kind of overseeing and coaching that. And there was a very last-minute conference call that I had to be on yesterday afternoon to get some more information before everything starts. So unfortunately, I had to be on that instead of this when they took place at exactly the same time. But I want to thank you all for your flexibility in being able to postpone this until today. I don't usually like, having to reschedule things like that. There are occasions in which it's kind of unavoidable. This was one of them. And, that's just kind of what it is. So I appreciate your flexibility. I appreciate, being able to wait a day. First module is kind of an easy one in this class anyway. So, I don't know that the lack of material is hurting people too badly, but we're getting there anyway, so we're great. So we are talking about Module 1 today, which is thinking like a programmer. And some of this stuff, especially for those of you who have taken some of my other classes before, I know not all of you have, but some of you have taken some of my other classes, and you will have heard a lot of this stuff before at some point in time, but I do think it's important to just kind of be reminded of it as we are kind of getting started here. So one of the things that I usually like to do when it comes to getting started in a new class and covering a new topic is to just handle some definitions. So I'd like to handle a handful of definitions as we're getting going here, just so we can all have a good understanding of them. So the first one that I'd like to talk about is just what exactly is programming. Right, so just defining the term programming as we're kind of getting started here. And I do kind of define it slightly differently in all of my classes, even though at the core it's the same, right? Because we have here the 5 things, which could be the 4 things if we take and combine math and decisions here. But these are the 5 things that all programming languages to some degree utilize: input, output, math, decision-making, and repetition. Right, so when we are programming, we are writing a sequence of instructions, an instruction being just a singular line of code. So we're writing a sequence of instructions that specifies how to perform a computation. And that computation can be purely mathematical. It can be alphanumeric. And when we say alphanumeric in that sort of sense, what we mean is that, we can be executing commands or scripts on strings, on sequences of characters. We could even be working with pictures or video. Right, a computation has a wide connotation to it, right? It's not just math, which is something that we often, associate with the term computation. When we're talking about programming, a computation could be many things, right? And, that's where we get that the word computer from, being something that does a computation. And so our computer is executing a sequence of instructions or executing a series of lines of code to do a thing, basically, right? Like when we're talking about computation, we can kind of break it down to the idea of an action, right? Our computer is following our instructions to do an action. And, we have input, we have output, we have math, we have decisions, we have repetition. Input obviously being the way that we get our data into a program, and that could be done from a wide variety of means, right? It could be done through the keyboard, could be done through a file, through a network, through some kind of sensor, right? Some way to get data from the outside world into the device that's doing the computing. And then, of course, if we have input, we need some kind of output, right? Output being the thing that allows us to, after the computations are done, get the data back out. And we can look at input and output really through sort of this combination of what we call the data cycle, right? So programs in general are run through the data cycle, right? We have an input, that goes into our computer. Our computer runs it through some sort of process. And after that process is run, we as the individuals who are controlling that computer or who are running that program, we need to be able to get the results of our process. And so in turn, we get our output. And so this is kind of the life cycle of our data as it goes into a computer. It's the process that turns data into information, the input, the process, and the output. If you might have heard me, talk about it in other classes, where we talk about data in terms of, for example, like cooking a chicken dinner, right? Like you go to the grocery store, you get a chicken. That chicken is, raw. If you eat it, it'll make you sick. But it is a good raw material. Something can be made out of it, right? And so when we look at the data cycle in that regard, that's kind of our input, right? When we have data that's an input that we're getting ready to run through a computation, it is typically raw data. Right? It's typically raw data. It's data that we have that we need to do something with. And so from there, we run it through some sort of process. And that process is essentially our program, right? It's the series of instructions that is performing our computation. Right? So that process could be one of many different things, right? It's just basically just whatever program we're writing. And then on the output side here, we get out information, right? The processed or the cooked chicken dinner for our data cycle here, it goes from raw data into being information, into being data with value. And so that's a pretty significant thing that we're looking at here. So that's our input and our output. Our math is simple, just basic mathematical operations, addition, subtraction, multiplication, division, right? These are all things that are done in all programming languages because math is kind of ubiquitous in computer science, right? One of the things that I will say a lot is that, the reason that we have computers in general or programming or anything like that really is just because math is hard, right? Like when we look at the history of computers, which is one of the reasons why I think it's important to look at the history of the computers, which we do in our CTI 110 class. One of the things that we see in there is that basically the very first computers that we had, way back at the, end of the 1800s, or mid to late 1800s, were basically just glorified computers that we could write some kind of algorithm via punch cards that we could put into the system that would basically allow us to do complex equations. Right, so nowadays, like back then, it would have been something that was very big that was doing these computations. We kind of went from like kind of small to enormous, back down to tiny again. Right, because since those first computers didn't have a whole lot of operations, they could do, think big typewriter. Kind of that size. Right, didn't look like a typewriter, but we can kind of say, roughly that size. But now, like all of the things that could do and way more can be done on a calculator that we could go to Walmart and buy for $3. Right, that fits in our pocket, and let alone our phones and things like that. Right. Decisions, being able for our computers to make decisions, check some sort of condition, and then based on whether or not that condition is true or false, run code accordingly. And then finally, repetition. And in this particular class, we discuss repetition in two different ways. We discuss it through recursion, and we discuss it through loops, which we'll talk more about that stuff when we get there. But it's just the ability to perform the same action over and over and over again without having to repeat yourself. One of the things that I'll talk about are some of the programming rules that are, acronyms that they've come up with, over time, right? And one of the big programming rules that we want to keep in mind as we're writing our own programs is something called DRY, D-R-Y, which is an acronym that stands for Don't Repeat Yourself. Right, so I shouldn't be writing big blocks of code multiple times when I can execute them via some sort of repetition, via recursion or via a loop. But out of that, one of the things that we can think about is, that's programming. What exactly is computer science, right? And, especially when you're dealing with Java, the whole concept of computer science comes up. I was kind of looking through your introductions in the Begin Here module. I saw, at least one or two of you had been working on, computer science majors at like other colleges and universities. I saw a handful of you have some experience with C# and C++, other programming languages. If you had a little bit of experience in C++, you'll see that C++ is really similar to Java. So I don't remember who it was that said that they had done a little bit of C++ before. But if you've done a little bit of C++ before, you should, it should be a little bit easier to pick up, because these two languages look pretty similar. C#'s a little bit different. I've done a little bit of C# myself. One of the big things that I like to try to get people to be able to do in programming is, if you have some experience with one language, then, one of the big things that we want to learn is how to be able to transfer that experience into other languages. I've done a little C# myself. I wasn't a huge fan of C# when I was programming in it, but I know, for example, the people who were talking about it in their introductions were talking about it in relation to Unity and game development, which is where I got my experience with it, is also through Unity and game development. Because my master's degree actually has a specialization in simulation and game development. And, one of the things that I discovered kind of through that is, because, just kind of as an aside, a lot of people come to me and they say, I want to be a game developer. Where can I go to be a game developer? And you can find game development programs, right? There are different colleges that have specifically, simulation and game development programs. And there are some things that you would have to consider if you were doing simulation and game development that you wouldn't necessarily have to do in a more generalized program. Things like, working with 3D models and stuff like that. But one of the things that I always say is, well, if you learn the basics, right? Learn the logic, learn the basic structure, learn modularity, learn how to be a programmer first, and then you can kind of start branching off into your specializations. And I think you'll take it up a lot easier as you get into those areas, right? Because just having the central structure of knowing how to program, from there you can find your niche, right? Whether it's game development or data analysis or software development or web application development or whatever niche you have, like what would be another one? Onboard systems programming. So the programming for things like, your refrigerator would use, that sort of thing. Which there is, especially in more modern appliances, right? They have logic boards where they've been programmed like, if it gets this cold, then cycle this off, cycle this on, so on and so forth, right? So all sorts of stuff. If you learn the basics, then you can kind of take and branch out and find your niche and find what you like doing. And so I think that's important. So that was all just like a real side pathway from the fact that I saw at least one or two of you had been in a computer science program somewhere. And computer science itself, it sounds like a big, heavy, mystical term. And, a lot of these universities, as someone who went to the University of North Carolina, I can tell you that it was done there. And a lot of these universities, it kind of feels heavy, right? It feels like a heavy concept. And they make it seem like a heavy concept. Although, I've actually seen in more recent years, there's one professor in particular at the University of North Carolina who has really made things a lot better in terms of introduction to programming from what I've seen, which is pretty cool. But computer science is just the science of algorithms, right? And algorithms, another big word that we hear used a lot, right? And if you don't have a lot of experience with programming, or you haven't been doing this much, or haven't been around this area much, your experience with what you know of algorithms comes from where you've heard about them. And I think a lot of people have heard of, like, for example, algorithms in movies where they talk about different things, or things like the YouTube algorithm or Twitter algorithms, right? Website algorithms that perform a certain action, right? But all an algorithm is just basically the sequence of steps that it takes to solve a problem, right? So an algorithm can be very simple, right? If it's a problem that can be solved in just, one or two or three steps, right? It's a very simple algorithm. Or an algorithm can be very complex, right? It can be, hundreds, thousands even lines of code to perform an action, right? So all we're talking about when we're talking about an algorithm is it's just a sequence of steps that specifies how to solve a problem. So if we take that and relate that back to computer science, if computer science is the science of algorithms, specifically computer-based algorithms, right, because it is computer science, then we break that definition down even further. And computer science is just the science of, or the study of, using computers to solve problems. That's basically it. Right? When we're talking about computer science, all of computer science is just basically using computers to solve problems. And one of the things that is kind of important for us to realize is that, doing these things, designing algorithms, writing code, it's traditionally very difficult. You can make a lot of mistakes while doing it. For historical reasons, programming errors are called bugs. And I actually have the reason why on the next slide here. And some of you might have seen this. Others of you may not have. Right? This is actually the very first, what they termed computer bug. Right? The very first computer bug is a moth. Right? That's and it was actually something that was discovered Admiral Grace Hopper. Right, a programmer in the Navy is said to have discovered the first computer bug, right? A moth flew into a relay panel. And when you have things that are, we're talking about, back in the 60s, 70s era here, right? And so, at this point, computers are still largely mechanical. Computers are, have a lot of machinery that are still running them, especially if you're needing to run them on a ship at sea. So if a large enough bug gets into the hardware there, it can gum up the works and cause problems. And so they actually, they took the bug and they taped it to the journal entry here when they documented it. I mean, we could see that it was extracted and documented at 15:45 p.m., right, which is around 3:45. And so we actually have this good record of the very first computer bug, and it's just a little kind of fun, whimsical story as we're talking about, the idea of solving bugs and problem solving with our algorithms, right? Another thing that we want to consider with algorithms, and I talk about this in depth. I kind of wish we had a class where we could talk about this a lot more. Things like algorithm bias or algorithmic bias. Basically the ethical questions that come up in programming and in other, sort of tech-based job situations, right? Because one of the things that we want to remember, and it goes, it kind of ties into the line that, our computers are just following our instructions, right? That's what we said an algorithm was just a sequence of instructions and that solve a problem. And, these instructions are written by people, right? You'll be writing a lot of instructions this semester as you're working on your programs. And people, whether they realize it or not, can bring their own biases into the problems that are being solved. Right? People are determining the problems that they're solving with their code, and people are writing the instructions to solve said problems, so they're writing them in their own way. One of the things that we find exceptionally challenging about programming is this idea that, there are dozens of different ways to solve the same problem. And then there's the idea that the way that you perceive a problem might not be the way that I perceive a problem. And then we determine what problems are worth solving, right? So there's a lot of choice, and there's a lot of personal input that is given to these programs by by individuals. And so we end up with writing programs that are influenced by human beings. Right, I think this is kind of an important thing to talk about because in general, we kind of think about computers as being sort of a, cold, analytical, just like Spock but a machine, right? But, the thing is that our computers don't think for themselves. Our computers just follow instructions. You see, the thing about computers is that, computers are dumb. Right? Computers can't think for themselves. Even if, we're starting to get more into an era of AI nowadays. Right? I'm sure. And I'm going to go ahead and make you all aware that I am aware, I'm fully aware of ChatGPT and its powers. Right, and we can say that, this is an example of a program that is smarter. But, not necessarily, right? Computers in general are dumb. They only do what we tell them to do. Even something like an artificial intelligence is only limited to the knowledge of what it encounters, what it's given. Right? The thing that makes an artificial intelligence or a neural network different than just a regular program is basically that it stores and works through new information that it's given. So it kind of learns in a similar way to the way that people learn, right? So, you go to class, you hear something new that you didn't know before, and you can either choose to add it to what you know, or you can accommodate it into what you already know. So it can basically change the way that you look at things, or can become a part of the way that you look at things. And that's essentially, what's happening with a neural network or an AI, right? Just on a, just sometimes on a much larger scale, right? Like if I took a neural network and I was trying to show it pictures of cats, right? It's going to learn kind of the general shape, the general outline, the general feature of a cat. And then if I show it a picture that's a little bit different, but it's still a cat, it might not recognize that picture because it doesn't fit the pattern of what it has traditionally been fed as being a cat. And so then I, as the programmer or whoever's training the neural network, in turn say, no, that is also a cat. And it just modifies the patterns that it's looking for to include these new specific things. And the more things it encounters, the more it might come into conflict with things that it knows as well, right? So if I show it a picture of a dog, right, there are shared traits. So based on what I've told it is sort of the pattern that it should be looking for as cat, it could say, oh, that's a cat, right? Like it's not going to automatically know that's a dog because it doesn't have a frame of reference for a dog. And so I basically say, no, that is dog. And it just takes these new patterns that it's just seen and accommodates them to a new learning model for now dogs, right? So even when we think about things like artificial intelligence and neural networks and things of that nature, they seem super smart, but they're still dumb, right? And I have an example here of computers being dumb, and it's one of the reasons why we have to be extra careful as we're writing code, because computers don't look at letters the same way that you and I look at letters, right? And that's a super important thing for us to consider here, right? Computers don't look at letters in the exact same way that you and I look at letters, right? If we look at the letter A here, we can see a lowercase a, or we can see an uppercase A. And as smart human beings, we know that both of those letters are the letter A. But to my computer, who is not smart, to my computer, who is dumb, these are two totally different characters. We have lowercase a, which it sees as the binary equivalent to the number 97. And we have uppercase A, which it sees as the binary equivalent to the number 65. Right, and if we did the binary for these, which we could, right, if we say lowercase a is a 97 decimal, we can do our binary equivalency for our octet. So that would be 0, 1. Let's see, that leaves me with 97 minus 64, which is 33. So that would be a 1, 0, 0, 16, 8, 4, 2, 1. Right, and so that's for our lowercase a. Right, if we were to see a lowercase a on a computer, the binary for that would be 0, 1, 1, 0, 0, 0, 0, 1. Right, our uppercase a, in turn, and I'm not asking you to do this, this is just a demonstration. Right, our uppercase a is the binary equivalent of the decimal number 65. So that's 0, 1, 0, 0, 0, 0, 0, 1. Right, and so we can see here, we see a big difference here in our decimal number. But when we get into our binary numbers in terms of what our computer sees, we actually have a very small difference, right? But it's still a difference. So our computer sees lowercase a and uppercase a as two completely different things. The only difference is this one bit right here being flipped. Right, the bit in our 32 place is flipped. In the lowercase a, it's a 1. In the uppercase a, it's a 0. A bit being the very smallest bit of memory that could exist, right? A singular binary digit, right? Which is where bit comes from. Binary, digit, bit. So this one bit makes my computer look at these two letters as two completely different things. And so this gets back to this idea that computers need us to be very specific in the instructions that we are writing. Right? So if it's uppercase, it needs to be uppercase. If it's lowercase, it needs to be lowercase. We can't use them interchangeably because our computer doesn't understand that. If it needs a punctuation mark, we need to make sure we put that in there. We can't leave anything out. and just assume, oh, our computer will understand, because it won't. So that's super important as we're approaching this. So one of the things that I recommend you all do is write pseudocode. I don't force you to do it. I probably should force you to do it and make it a part of assignments. I don't force you to do it, but I highly suggest that you do it. And, as we're doing programming demonstrations in class, we will start them out by doing some pseudocode and some planning. When we're thinking about pseudocode, we can kind of think about it as pre-writing for when you're writing an essay. Just kind of getting your ideas on paper and making sure you kind of understand the structure and the logic behind what you need to do to be able to implement this. And all this essentially does for us is it just takes code and allows us to just kind of get it out there in a low-stakes format, just so we can have an understanding of what we want to write before we start wasting a lot of time writing code. It's just as simple as that, right? So I suggest that I don't make you do pseudocode, but I highly suggest that you just take some time, sit down with a piece of paper and a pencil just in front of you and just say, okay, what does this computer need to do when it is solving my problem? What are the instructions I need to write? What are the data structures, which we'll talk more about that as we go through. What are the data structures that I need to use to make this all work? And so once you kind of get through that, you can start writing the code. When we're talking about programming languages can basically be boiled down into two parts: logic and syntax. Logic is basically the how, and syntax is basically the what. Right? So the syntax is stuff that I can get out of a book, right? It's kind of like the rules that you learn in English class for how you write a sentence. Right? There's got to be a period at the end. There's a comma after your conjunction, or, whatever, right? Like, it's a series of rules that allow you to write a programming language. And every programming language has a different syntax. Java's is different from JavaScript's, is different from Python, is different from C++, is different from Ruby, and so on and so forth. But syntax is something that you can learn from a book, or it's something that you can easily look up. Where things get kind of a little more challenging is this idea of logic. And that is when I use specific syntaxes. Right? One of the analogies that I use a lot of times as I'm describing logic is basically we can teach syntax and we can talk a lot about syntax. Logic is kind of harder to teach as far as all that goes, which is why we do a lot of projects. It's kind of gaining your logic through practical application. Right? I'll say that I can give you the pieces. When we're talking about the pieces, we're talking about the syntax, right? We could talk about syntax in different ways that we can implement that syntax. But at the end of the day, I'm going to give you all the puzzle pieces, and you have to figure out your way to get them to look like the picture on the outside of the box. You have to figure out your order that makes the most sense to you. You have to logic through and figure out how to make it work, how to solve the problem using this syntax that you're given. And, again, one of the things that makes that challenging is there are dozens of different ways to solve a problem using a programming language. We're learning Java in this course. Obviously, it's Java programming. It's a high-level language. High-level languages are closer to English than what we call low-level languages. So other high-level languages are Python, C, C++, Ruby, JavaScript, Rust, Go, Erlang. There's all sorts of languages that are out there. Low-level languages are things that are closer to machine code, closer to computer code. So when we think about things like assembly, assembly is a low-level language. Another thing about high-level languages is that high-level languages are portable, meaning that we can run them on different kinds of computers with little modification. Right? So I can write a program in Java. I can run that computer on a Linux machine. I can run it on a Windows machine. I can run it on a Mac. A-OK. Right? No issues. It just might need to be compiled a little bit differently for the different platforms. Right? So we can talk about interpreters and compilers very briefly. And in this course, we really don't get into compilation and interpretation very deep, right? Since we have our online IDE, Replit, that handles it for us. We don't have to worry about it in that sort of way. But an interpreter just reads the instructions and does it. And then the compiler reads the entire program and translates it basically into machine code before it starts running. And we can actually take that and execute or create an executable source code bit from it, or a .exe. Right, and so Java's both. Java's both interpreted and compiled. So we can see that both ways. And what we're doing through Replit is actually interpretation. But it does generate a class file and all this kind of stuff. So it is like it's doing compiling for us, but it's mostly interpretation. So let's have a look here at Replit and just see how we use this platform. Then we'll go back to our other thing. I just want to, I want to not talk for a few minutes. Or just not talk about slides for a few minutes. I'm still going to be talking. But we're not going to really go much into how we use, or actually much into code today. We'll save more about doing more code next week, and you'll see why in just a moment. I just want to talk about creating a Java Replit and working with it. You can see this is the page you'll land on after you log in to Replit. You can see I have 3 create buttons here. I have one up here on the left-hand side, one here in the middle, a little plus sign button here on the right-hand side. All 3 of those do the same thing. So I can click create, and in search templates here, I'm going to type in Java, Java. And you'll see there are multiple different sorts of templates here. We're just going to be, for the most part, right? In the last module, we get to use a different one, which is going to be this Java Swing. But up until that last module, we're just using plain old Java Replit. You can see here, blue icon with what looks like a little cup of coffee on it. Just the word Java, created by Replit. After we click that, we get the ability to title it. It'll give you a just randomly generated title by default. Or you can type in my first program. And I do this every semester, so I'm going to have to type in a unique name. So my first program, Sp23. And so this is why we're not going to dive too much into the programming aspect of it all today, because it actually gives us a little bit of boilerplate for what we're working with here. Right, and we'll talk more about kind of what all of this means when we get into the next module, but we see basically everything that you see here except for what's on line 3 here, which I can comment out briefly, is a requirement of Java. And we'll talk more about this in the next module as well. But we see here this class main. Java is object-oriented, which means that everything is built within, which partially means everything is built within classes. So all files that are .java files have a class to them. And the class for a particular file is going to be the same name as the file. Right? So we see by default we get a file called main.java here that's given to us by Replit. You don't have to touch this over here. Right? A little later on in the semester I'll show you like how you can do different things with it. But you don't have to touch the name here. You can just leave it main.java and class main here. Now one of the things that does get confusing though is that this word main here and this word main here have nothing to do with one another. They're two entirely separate things. One of the ways I can tell that is that main here is lowercase and main here is uppercase. And as we just learned, right, my computer sees lowercase and uppercase as two completely different letters. And so these are two completely different things to my computer. Right, this main here and this main here. Every single Java program that is designed to execute, to run some code, will have a void main function. This is where you put all of the code that you want to run. You can have other functions, but those other functions will not execute unless you call them inside of this main function, right? And that's one thing that we'll kind of look at as we get into writing our own functions. But just for proof right now, I can write a public static void something function and system.out.print hello. And as we run this, nothing will happen on the output. Right? We get our two lines here where our compilers worked to compile and interpret our code. But we don't get any output. We'll only get output if we have some reference to something inside of this main function. So for example, if I call my something function by just typing in its name like so, then I get hello on my output, which you see over here. Hello. Right, so we can run code in here directly, like that system.out.print line, which is how we get text to come to our console over here. So we can run code in there directly like this, which gives us our hello world. Or we can write other functions and put calls in there to other functions. But we have to put a reference to those other functions inside of main for that code to actually execute. System.out.println or system.out.print are ways that we put text onto or into the console just on its own. And that basically is just, kind of the way that your coding lab assignment for this module works. It's easy for this one. I basically just want to see that you are able to get in Replit, put in code, and have it, just work, right? All you really have to do is copy and paste for this first module. You know what? Just to keep things kind of short and wrap it up for today, I think I'll save the other bit that I wanted to say for next time. So I think we'll go ahead and wrap it up here, right? It's just a few slides that I have. That's another bit that I want to cover, but I think we can kind of put a pin in it, talk about it at maybe the beginning of the live class next time. It'll go really quick. We've almost hit our hour mark, though, and I know it's late in the day on a Tuesday of all days, right? So I'm sure, at this point, anybody who's watching probably getting a little groggy, probably getting a little leery, a little weary, rather. So we'll go ahead and wrap it up here for today. If anybody has any questions that are here with me live, and I should say, too, right, as you're submitting these assignments, submit the URL that you get. That is a public URL, right? Mine's highlighted green up there now. That's a public URL. So if you send that to anybody, they can view your code, they can run your code, but they can't edit your code, right? So if you take that link and just put it into Blackboard and send it to me, then I'll be able to view the code that you wrote and see the output that I get from it. And that's fine. If you invite me, I can actually, if you invite somebody using this invite button over here, then they can actually collaborate on your code, which don't necessarily want, to give somebody else the ability to change your code when it is something that you are sending in for a grade. So with that being said, that's where we'll wrap up for today. We'll just give it another minute or two just in case anybody who is here with me live has any questions. Thank you all for watching. I will hang out in the chat for just a couple minutes just in case there are any questions that come through. If you're watching the recording and you have a question, please send me an email or a Teams message and I will answer it as best as possible, as soon as possible. But that's all that I have for you for today. No worries. Thank you for coming, Ariel. Thank you so much. Wonderful, wonderful. Glad to hear it. Thank you all for watching, and we'll see you next week. Hopefully on our regular day next week. Thank you.